Last time we were talking about, remember we talked about the zeros of polynomials. We talked about, I think, maybe turning points. I can't remember if that was last time or the time before. Oops. Let's see. I want to see what we got. Okay. Tell me real quick, how many turning points, you're going to have to maybe think about this just a little bit. How many turning points could this graph have theoretically? 3. Okay, that's how many turning points? That's correct. How'd you get that?
Well, you get x squared as the highest one, first one, then x squared times x squared, x to the fourth, and then you only have n minus 1 points.
There you go. Okay, good. So if we were going to write out this polynomial, if we were going to expand it all out, I mean, the whole thing, that'd be kind of a lot of work to do. I mean, not a lot, but it'd be a decent amount, an appreciable amount of work to do. But if we're trying to figure out what the maximum number of zeros or turning points is, all we care about is the leading term, right? The leading term gives us a lot in a polynomial. It gives us the degree of the polynomial. We can use the leading coefficient test to know what the end behavior is, right? It tells us the maximum number of turning points. So if I were going to expand this whole thing out, when I expand out this part, I'm going to get an x squared plus other stuff, right? Everybody agree? And we don't really care about the other stuff. So 2 times that is going to give me a 2x squared. And then times another x squared is going to give me 2x to the fourth plus lower stuff, right? So the degree of the polynomial then equals 4, right? Biggest power of x. So if the degree is 4, then the maximum number of turning points is going to be 1 less than the degree. Everybody get that? It's going to be 3 turning points. Give me 1 to 5 on that. We good? Okay. What's the maximum number of x-intercepts we could have? 4. Yeah, it's just equal to the degree of the polynomial, right? Okay, good. Good. So then based on what we just did, what about the end behavior? Why don't you guys vote with your fingers here? That's first the 1, 2, 3, and 4. Everybody look at that and think about it for a second and register your vote. There you go. Yeah, I thought you said 4 at first. Yeah, there you go. Good. Good, good. What do we got? Yeah, okay, good. I'm seeing lots of 3s. That's good, right? We know the leading coefficient is positive and it's an even power of x. So what's that telling us? That's the end behavior for an even function. And if it's positive, they're opening up. If it's negative, they would have been flipped and opened down, right? So this is telling us, this leading term here is just telling us that the end behavior is going to be that. Now, what happens in the middle? Who knows? Could be crazy. It could do all kinds of flipping around and have peaks and valleys and things, but we don't care about that. With the end behavior, we just want to know what's going on as x approaches negative infinity and positive infinity, right? So this one would be then 3, third option. Okay? What are the x-intercepts? Now we got to talk a little bit more about this one, but think about it for a second. Discuss it with your neighbor if you want to. That's fine. But take a minute or two and see if you can come up with the x-intercepts. What are the x-intercepts? Okay, what's the verdict? What do you think? X-intercepts. How are we going to find x-intercepts? How do we find x-intercepts back in Unit 4 when we had quadratics? What did we say about x-intercepts? X-intercepts, there's an important relationship here dealing with x-intercepts, right? Well, think about it in terms of a graph. That's always helpful. What's going on, if you thought about a graph of a function and you were trying to identify the x-intercepts, where would you look?
Where y equals 0.
Okay, where y equals 0, right? Where it's crossing the x-axis, which is always where y equals 0, right? Okay, so y is just f of x, so we're trying to find, in other words, we're trying to find the zeros of this function. Where does the function have a y value of 0? Because we know x-intercepts always have a y coordinate of 0, right? So x-intercepts are always interchangeable with real zeros. Okay, give me 1 to 5 on that concept. We've talked about that one, but is that ringing a bell? Okay, so how do we find zeros? Well, if I'm given a function, how do I find the zeros? What are the algebra steps I would go through? What's my strategy or my approach? What are you going to do? No? How am I going to find the zeros? What does that word mean, the zeros of a function? Okay, maybe we better review this little concept a little bit. Okay. The zeros of a function are where, when I say where a function equals something, I mean x values, right? Are where. So the x values where the function equals what? 0. That's it. The zeros are where the function equals 0. Okay, so what am I going to do? What are the algebra steps I'm going to do to find the zeros if I'm given that function? Set it to 0. There you go. Just set it to 0. So to find the zeros, and the real zeros are going to be the x-intercepts, and that's what we're looking for. Let me back up a little bit here. I'm going to color code this. Okay. Now, we did a lot of stuff that looked like this back in Unit 4, where we would factor a function and then set once I have a factored equation set equal to 0, I could always find the solutions, or in this case, the zeros, right? Same thing as solutions. Where does this equal 0? I could find those by applying the zero product property. That's all I've got to do here. So what are the solutions to this equation? Like what are the solutions that come from that factor? 2. Yeah, how did we get 2? You're right. There you go, right? By the zero product property, remember the product of factors can only equal 0 when we're multiplying by 0, right? So when I have a factored expression set equal to 0, all I have to do is just find the zeros of the individual factors. In other words, what are the values of x that are going to make the orange and the green factors equal to 0? Okay. Well, the orange one, that's pretty easy. X minus 2 equals 0 when x equals 2, right? So we get 1, 0 at x equals 2. That's a real 0, so that constitutes an x-intercept, right? If the zeros are real, they show up as x-intercepts on a graph. Now, if they're imaginary, obviously those don't show up as x-intercepts because imaginary numbers don't show up on the x-axis, right? Only real zeros correspond to x-intercepts. So we found there's one important piece of information. We get an x-intercept at 2, okay? What about the green one? 3, okay, 3 is one option. What's the other option? Yeah, and how are we going to get that? There's a couple ways we could go about this. So I've got this thing in factored form. If I want to find the zeros of a factor, I can just set that factor equal to 0 and then just solve that mini equation, right? We didn't even write it down over here because it was so simple, but technically what we did was we set x minus 2 equal to 0 and solved. But that's just, I mean, it's just not even worth writing it down. It's so simple. Now this one's maybe just a little bit tougher, so let's write this one down. If I set that factor equal to 0, that's the equation I get, right? So I've got to flip into algebra mode and solve that. Now what are the steps to solve that equation? Add 9, and I'm doing this because look, I can point to a single x so I can isolate it, right? So I add 9 to both sides, and then what? Square root, sure. And when I square root, I have to include a plus or minus, don't I? So I get x equals plus or minus 3. Okay, good? Anybody see that? Okay, the other option we would have had here, and for you guys especially, I wouldn't do this. It's not necessary, but I could have taken this original function up here, 2 x minus 2 squared times x squared minus 9. And I could have factored it a little bit more. I could have factored that x squared minus 9 using a difference of squares, right? Because that's just x squared minus 3 squared, right? So then the 2 stays the same. The x minus 2 squared is already done. But I could break that one down into what two factors using difference of squares? X squared minus 3 squared factors into, yeah, good, x minus 3 times x plus 3. And all we're doing is we're just using our factoring pattern. A squared minus b squared, right, is just a minus b times a plus b. Either or, you can flip-flop that. Okay, give me 1 to 5. Is this all ringing a bell here? Are we good with this? Okay, good. So then we could have broken this up into x plus 3 times x minus 3. It all equals 0. And now when we apply the zero product property, look what we get. We get x equals negative 3 or x equals plus 3, right? So those are two different approaches. Which one should you do? I mean, they both work, but man, I'd do that one, right? That's a lot easier, isn't it? So you kind of have an option here. When I'm trying to simplify, factor the left side of this equation, you can kind of bail off the factor train whenever it's convenient, right? We don't necessarily have to break these apart all the way if we don't need to, right? I could have just said, okay, well, I don't, and the next time you do this, you probably don't even have to write that out. You could just look at this factor, x squared minus 9, and do it in your head. And say, what would the zeros of that be? If I set it equal to 0, aren't I going to get plus or minus 3 out of that? Rather than having to rewrite another step and factor it explicitly. Just easier just to solve the quadratic and get two solutions out of that because it's so easy to solve. Okay, does that make sense? Okay. All right, so we got the x-intercepts then. Negative 3, 3, and 2, right? That's what we got. Okay, so now, how about this? At which zeros does the graph of the function cross the x-axis? What do you think? So maybe here, let's look on the next page. Maybe it's useful to think about it being completely factored for this part. Okay, what's our rule? When do real zeros cross the x-axis? Remember what was our?
When the multiplicity is odd.
Okay, when the degree of the factor is odd, right? If it's to the first power or the third power or the fifth power, then the zero of that factor is always going to cut through the x-axis. And it's going to cut through the x-axis like the parent graph would, right? So in this case, I've got an x plus 3 to the 1 and an x minus 3 to the 1. So those are going to cut through. Those are linear factors, right? So those are zeros that are going to cut through the x-axis like lines do. Okay, when does a function bounce on the x-intercept? Even powers, right? It's going to bounce just like even parent functions do. So here we've got an x minus 2 squared. We know that that one's going to bounce, isn't it, right? Because it's an even power of x. So at positive 2, it's going to bounce off the x-axis, and at negative 3 and positive 3, it's going to cut through the x-axis. Okay, so the graph of the function crosses the x-axis at negative 3 and 3. At which zeros does the graph of the function touch the x-axis and turn around? Well, the way we say that, remember, we just call that bouncing. That's going to be at x equals 2. Okay? So how would I find the y-intercept of a function? X-intercepts, you told me, are where y equals 0, right? So what's true at y-intercepts? Think in terms of a graph. Y-intercepts are where the graph crosses the y-axis. Yeah, everything on the y-axis, every point on the x-axis has to have a y value of 0, right? So if I want to calculate what are we looking at here? The y-intercept of this function, I'm just going to evaluate it at 0, right? So for this part, find the y-intercept, then we're just going to do f of 0 equals, well, what's that going to give us? 2 times, what's the value of that factor when x is 0? X minus 2 becomes what? Negative 2. So I'm going to get a negative 2 squared times 0 squared minus 9. Isn't that just negative 9? Simplify that, and that's our y-intercept. So that's just given us 2 times 4 times negative 9. So 8 times negative 9, negative 72. Okay, anybody buy that? Okay, now the symmetry stuff. Okay, I'm gonna show you just a couple things about this. I don't want to spend a ton of time on this right now. This is really more of a pre-calc topic that you'll come back to in pre-calc, but for you guys, I want to just introduce it a little bit. So add this to your notes. This isn't going to be something there's not really room in the notes template for this, but if you need to break out a piece of notebook paper or put it in your Algebra 2 notebook, let's talk about this for just a second here. So here are the kinds of symmetry we can have. There's two kinds. We can have even symmetry or we can have odd symmetry. Okay, even symmetry, if we look at a graph that has even symmetry, a classic example of that would be y equals x squared. So even symmetry is always going to be folding symmetry about the y-axis or line symmetry about the y-axis. That's what we mean by even symmetry. So there's an example of a function with even symmetry. Here's another example of a function you're not familiar with that has even symmetry. If I look at a cosine function, you'll see that next year. It has folding symmetry about the y-axis, right? So those are all examples of even symmetry. Okay, what's our test for even symmetry? This is important. Our test for even symmetry is just this. If I substitute negative x into the function and it doesn't change the function, then that's even symmetry. You can always apply that test, and it's always pretty easy to do. Okay? So for example, what if we wanted to try, well, we'll come back to some examples in a second. Okay, what about odd symmetry? So odd symmetry is rotational symmetry about the origin. So an example, like the classic example, would be x cubed. Right? It's got that rotational symmetry, meaning I can spin it 180 degrees and it lines up with itself. Another function you're not familiar with that has odd symmetry would be the sine function that you'll see next year. Oops. There we go. Hang on, let me redraw that. That's pretty bad. Like that. I can actually spin that thing 180 degrees and it overlaps with itself. Okay? The test for odd symmetry is this. F of negative x. So if I substitute negative x into a function, if I get back the opposite of f of x, then that's odd symmetry. Okay? So let's try a couple functions here and see if we can see a pattern coming out of this. Okay, so let's see. I'm going to remind you about the tests. So even f of negative x equals f of x. Odd f of negative x equals negative f of x. So let's try a couple. How about this one? Okay, there's a function. Let's test the symmetry on this and just see what the outcome is. So all we have to do is plug negative x in for x and see if either one of these two things happens. So if I do that, whoops. How am I going to do that? What's f of negative x? If f of x equals x cubed minus 2x squared plus x, what's f of a? What's f of a? If that's f of x, what's f of a? But if f of x is x cubed minus 2x squared plus x, all that's doing is just telling me what's the recipe that's acting on my input values. What if I input an a? What's the output going to be? Let me write that down. So f of a means that we're going to follow the same rules that we did when we were evaluating functions all year, right? If I'm going to evaluate a function, then every place I had an x, I'm going to open up an empty quantity. Remember doing this stuff, right? And what am I going to plug in instead? An a. So I'm going to get a cubed minus 2 times a squared plus a, right? What would I get if I evaluated this function at -2. Say it again. Just put -2 in for the variable again, right? So every place I used to have an x, I'm going to put in the quantity -2. And what would I get if I simplified that? What is the quantity -2 cubed? -8, right? I got to cube the -1 and cube the 2, right? Because it's in parentheses. So I get -8. -2 squared is 4 times -2 is -8, and then plus -2 is minus another 2, so what I get, -18. Okay. All right, so now let's try f of -x. We'll apply that same thinking to f of -x. So every place I used to have an x, I'm just going to plug in the quantity -x. So what's the first term going to simplify to? What do you think? Carson, what's the quantity -x cubed? -x cubed, right? I'm going to get -1 cubed times x cubed, which is -x cubed, right? What's the second term going to be? Allie, what's the second term going to be? What's all this going to give me here? Okay, now I'm not squaring the 2, right? I'm only squaring the stuff in parentheses. -2x squared. Everybody see that? Because the -x squared, if I square the quantity -x, I'm just getting x squared. -x times -x is positive x squared, times -2 is -2x squared, plus -x is -x. So let's look at this. That's f of -x. Is that equal to f of x? Thumbs up or thumbs down? Thumbs down, right? So it's not even. We can cross out that possibility. Is this equal to the opposite of f of x? Thumbs up or thumbs down? Thumbs down, right? So is it either one of those? No. The answer is it's neither. It's neither odd nor even, okay? Let's try another one. See if you can see a spot a trend here. Okay, so our test for symmetry, what do I do? If I want to test the function for symmetry, what do I input? -x, okay. So f of -x, every place I used to have an x, I'm replacing it with a -x. And what is this going to give me? Aubrey, what am I going to get from the first term? Okay, well, what is -x to the fourth? X to the fourth. Okay, good. Times 2. 2x to the fourth. There you go. And again, quick reminder, another way to think about this would be anytime I take any negative quantity to an even power, it becomes positive, doesn't it? Right? Negative quantity to an odd power stays negative. Okay, let's see. Kylie. What about this one? So -x quantity cubed is what? -x cubed times -6 plus 6x cubed. Okay. Oh, whoops, I wrote that down wrong. Hang on, that's supposed to be squared, not cubed. Let me go back here. That was supposed to be a squared. I made that squared on purpose. So now, again, Kylie, what's that going to be? So -x quantity squared is? Okay, good. I'm going to get -6 times a positive x squared. And the 11 just stays the same, right? Okay, what did we find? What's f of -x equal to this time? f of x. Yeah, how about that? So we found f of negative x equals f of x. So this one has, what was my color up here? It was blue. So this one has even symmetry. Okay? Let's try one more, and I'm going to see if you can see a pattern. Let's try this guy. So g of x equals negative 3 x to the 5th plus 2x cubed plus 4x. Okay, we'll do our test for symmetry, so we'll evaluate the function at negative x again. So every place we used to have an x, we're substituting a negative x. First term, what am I going to get from the first term this time? Grace, what's the first term going to be? If I have negative x, the quantity negative x to the 5th, what's that going to be? Okay, good, because I'm going to get negative 3, and if I have a negative quantity to an odd power, it stays negative, doesn't it? So overall, that's going to turn into 3x to the 5th. Next term, Jack, what's the next one going to be? Negative x, the quantity negative x cubed stays positive, or stays negative or turns positive? Stays negative. So then we're going to get negative 2 x cubed, and then finally 4 times negative x is just minus 4x. So what's the outcome there? That's opposite, isn't it? Right? I could rewrite that if I wanted to. If I factored out a negative sign, if I factored out a negative sign, that's a weird thing to do, but factoring out a negative means I'm going to undistribute a negative from each term. It's like I'm dividing each term by negative 1 to see what the result is, what's left behind. So that's going to have to be a negative 3x to the 5th, isn't it? Because negative times negative gives me my positive, right? This one's going to be a positive 2x cubed, and that one's a 4x. Well, look at that. That's just f of x, right? We get, or g of x, sorry. So g of negative x equals negative g of x. So what do we know? That's odd, right? Okay, can you think of any reason why maybe we call this kind of symmetry odd symmetry? Yeah, look at that. If we've got a polynomial that has only odd powers of x, 5, 3, and 1, you don't even have to do the test. You automatically know it's going to be odd. How about that? That's how it gets that name. What about the even test? Well, look at this example. 4, 2, and what's the power of x that's going with 11 there? 0, yeah. Right, it doesn't show up x to the 0 is just 1. Well, what's true of those numbers? 4, 2, and 0, those are even powers of x. And so if I have a polynomial that's only built with even powers of x, I know the symmetry is even. Now, what happened to the symmetry when I mixed? When I had odd powers and even powers, it breaks the symmetry and you get nothing then. You get neither symmetry. Okay, does that make sense? Okay. That's a really, really good trick. When we get to rational functions, if we get there, I'm really hoping we do, I'll show you how you can extend this thinking really quickly to figure out the symmetry of a rational function, which is just a polynomial divided by a polynomial. Well, actually, I'll just tell you. Like, see if you could, because who knows if we'll get there, but I want you to be familiar with this concept. So what if I had, and we haven't even seen these things yet, so don't panic. I mean, this is going to look pretty strange. What if I had the function r of x equals x cubed minus 3x? over x squared plus 4x plus 6. Okay, what's the symmetry of the top? Odd. Okay. What's the symmetry of the bottom? Whoops, hang on. Let's get rid of that term. What's the symmetry of the bottom? Even, right? What's your intuition tell you, I think you're probably going to get if you divide an odd symmetry by an even symmetry? What do you think? There's no way you would know this. I'm just curious if you're, well, if you just made an educated guess here, what would you think? No, it is one of them. I'll tell you that. It's odd. Yeah, it's odd. So odd divided by even is the same as even divided by odd, and the answer is odd. Okay, what do you think happens if you divide even by even? What do you think? Even. Okay, what if you divide odd by odd? It's also even, yeah. So how can you think about this? Can anybody come up with a quick trick? I'll give you a hint. It's similar to our sine rules. Like dividing, if you're dividing positives and negatives, you have some rules, right? So what's our rule here? Yeah. Here's a quick way you can kind of just always think about the sign. Think of odds as being negative, right? And the way I remember this is like -1 is an odd, but just think of the odds as being like a negative number and the evens as being like a positive number, and you're going to follow the very same sign rules, even if you have some really complicated series of functions. You can always just follow the same kind of sign rules you would with, with positive and negative numbers. Okay, I got off track a little bit there, but I just wanted you guys, and I'm not going to have you do, honestly, I probably won't have you do any problems on this, but I just wanted you to see it. Oops. Are we out of here like in real soon? 1 minute? Okay. All right, so I put the assignment up. I want to go through just a couple more. I know that took a lot longer than I anticipated. We'll go through just another couple quick examples, and then I'll let you guys work on it tomorrow in class. How about? Okay, get questions answered.